Team in this session, the team from Aachen.
Well, hello everyone and welcome to Team Aachen's iGEM presentation. Taking part in iGEM, we all want to save the world, or at least make it a little bit better. So in the process of finding our idea, we looked at global issues that humanity will have to face in the future. And one of these issues is water scarcity. Every year, the World Economic Forum compiles a list of the crises that would have the biggest impact on the world. And water is number 3, right after weapons of mass destruction and extreme weather events. And thinking about water scarcity, we found that seawater is the first thing that came to our minds. And looking at the world map, it's blatant that seawater is abundant, but it's undrinkable due to ion contamination, mostly sodium chloride. This type of contamination is also present further up in the water cycle, rendering huge amounts of fresh water undrinkable. Causes of this contamination are mining wastewaters, fertilization and fossil irrigation, chemical industry wastewaters, and potash industry wastewaters.
So, in Germany we are facing the problem, the burden of ions as well. And especially potash mining has motivated us to work on water pollution. We have visited the main region of potash mining in Germany, and what we found there both impressed and first of all shocked us. There, the industrial processes generate high amounts of salt, which end up to be dumped on fields, creating massive mountains consisting of nothing but salt. And just to give you an impression, with over 200 meters, these mountains are more than 2 times higher than, for example, the Statue of Liberty in New York. So, together with the rain, these salts are later on flashed out into our rivers and groundwaters. And additionally, the saline wastewater is induced directly into the affected rivers, destroying the biological diversity permanently. In the river Werra in Germany, for example, over 90% of the ground-living organisms have been suppressed by the high salt concentrations. And the reason for this is saline wastewater. And we have asked ourselves, what can we do about that?
To assess this problem, we looked for solutions in our most valuable resource, biological diversity, and found out nature already has an answer: bioaccumulation in plants. This is the mechanism plants use to defend themselves against harmful substances. They sequestrate these harmful ions and molecules inside their lysosome-like compartments, their vacuoles. Regrettably, plants are not a perfect solution. They do not grow easily on liquid media, they take a long time to grow, and they are not easy to replenish. That's why we search for another eukaryotic organism, Saccharomyces cerevisiae, or commonly known as budding yeast, which fulfills all these requirements. It grows easily on liquid media, it has a vacuole, it is natively halotolerant, and it's a model organism, which means it's well documented and it's easy to manipulate. Therefore, having all these arguments in mind, we decided to integrate the plant mechanism into the yeast. Through long hours of research, as every iGEM team does, we found out what happens with the sodium once inside the cell. Controlling the efflux, we have the sodium ATPase ENA1, as you see on the presentation, and the sodium proton antiporter NHA1. Controlling the influx into the compartments, but just mildly, we have the sodium proton antiporter NHX1. The natural response for yeast when it's under salt stress, it's mostly efflux. Just a little bit stays in the cell. Therefore, we wanted to include the mechanism of the plants inside the yeast, and we took up 2 strategies to make so. We knocked out the efflux mechanism, and we integrated the plant ion transporters. Taken from the plant Arabidopsis thaliana, we integrated the modified sodium proton antiporter ATNHXS1 and its coupled fueling counterpart, the proton pyrophosphatase AVP1. This and a couple more genes, we included them in the iGEM BioBrick repository to build up a little bit the limited BioBrick library for yeast. Rounded up, we integrated a sodium uptake into the yeast vacuole and increased its driving force while keeping the ions from getting out again. This design, we called it Water 2. This exact compositions of channels and transporters had never been done before. That's why we decided through research again to simulate this system kinetically to be able to determine if it's going to work. Then, we had to take into account different mechanisms that were into play in the system. First, uniporters, as our proton pyrophosphatase, ABP1, antiporters, as our sodium proton antiporters, difficult name, sorry, ATNHXS1 and NHX1, and ion diffusion through the plasma membrane, and ion influx, that's a complex of channels, transporters, and ion diffusion, which was simulated through a single substrate Michel has mentioned reaction. And that all together, with experimental values that we found in literature, and then integrated into MATLAB and biology, created this model. Complex enough as it seems, it gives us the answers we were looking for. We found out that it doesn't need a staggering amount of time to come to equilibrium, and we also found out it is mathematically possible to have a sodium uptake in the vacuum.
So, we wanted to design an application for our salt walls, and therefore we went into contact with wastewater treatment plants and industries. And we were confronted with two main tasks we had to focus on, regarding the safety and the after use of our yeast. Number one was to prevent the exposure of the yeast from the environment. And together with wastewater treatment plants, we considered membrane technology to be a candidate for the containment of the yeast. It is a well-established and rather energy-efficient method which could be easily integrated into the industrial application of salt walls. And to prove this concept in small scale, we conducted an experiment and tried to separate water and yeast with an ultrafiltration membrane which was provided by GE. And the result was outstanding. If you look at the picture here, you see that the yeast were easily removed completely and our test liquid got crystal clear after membrane treatment. So we can mainly tick off our first task. The second task was to depict further uses of our cells, which are pumped up with salts. So we obviously cannot just throw them away and we have to come up with another solution. And one possibility is to use the nutritional value of yeast and add them to digesters of wastewater treatment plants. There, the bacteria will have enhanced biogas production due to the yeast, and this can be transferred into electrical energy. Afterwards, the bacterial sludge is burned anyway, which would leave behind dry salt in our case. And the salt can either be recycled into chemical processes, or it has to be stored permanently. However, this is backed up by a new way of energy production. So, as you may see, we have put high efforts into considering our impact on the world and shaping salt walls with the input from people from all kinds of backgrounds. We have discussed wastewater treatment strategies, genetic engineering and biological education with politicians in Germany. We considered the impact of salt walls with students, researchers and citizens suffering from water salinization. We taught students about synthetic biology and talked to the government to make a change in biological education. We were part of wonderful collaborations with many iGEM teams from all over the world. Some of them are sitting here, very glad to see you. And we discussed the safety of our approach and our lab work with experts. Sixth point is, we discussed possible applications of our salt walls with water treatment experts. And last but not least, we visited industries who were committed to rethink wastewater treatment with us and luckily shared their data with us. So, integrated human practices were a big part of our project, and we just want to point out this work was a lot of fun. It was a lot of work as well, sure, but getting in contact with so many people from all kinds of the society really shaped and broadened our horizon along our journey. And on this way, we were mainly confronted with three questions. The first one was if the yeast are actually able to grow in saline media. Secondly, the people asked, don't the cells burst when taking up so many ions? And the third question was, how effective is the whole system?
This leads us to our results. The first question was pretty straightforward to answer. We inoculated saline medium with yeast. With saline we mean 0.6 molar sodium chloride concentration, that's about seawater level. And yeah, we inoculated yeast into a medium and put in the growth profilers and recorded growth curves. As you can see here, the wild type at the top grows fine, and the wild type in saline medium a little bit less naturally, because sodium chloride is toxic to the cells. But still, they grew okay. The second question, oh well, no, I forgot. We were even able to increase halotolerance with a single vacuolar mutation. Here you can see our mutant at the top in saline medium and our wild type again in saline medium. And note that the growth of the mutant starts earlier and does not plateau like the wild type does. And this was possible due to the mutation of AVP1, we mentioned earlier, the vacuolar driving force pyrophosphatase. The second question, don't the cells burst? We also answered with a little experiment. We let the yeast grow in 1 molar sodium chloride medium this time. That's almost double the concentration of salt water, seawater. And afterwards, resuspended them, isolated them and resuspended them in double distilled water. So huge osmotic shock. And as you can see, the cells are still intact, even though there is some cell debris in the background, if you look very closely. And then lastly, but most importantly, our third question. Does this work? Is it effective? Can yeast take up a notable amount of sodium? And our front-runner mutant that we designed and executed following a model was actually able to take up, oh no, I forgot about the wild type. Well, the wild type was able to accumulate 8% of the sodium in the medium, showing its natural halotolerance and accumulation as a defense as well. But our front-runner mutant was able to accumulate 31% of the sodium in the medium. 31%, that's not bad. And but we found out that one of the transporters we knocked out actually had a different effect than expected. So here you see our initial design again, and in the bottom left, the NHA1 sodium proton antiporter. And we found out that if we did not knock out this antiporter, we would actually have a high uptake. We called this design Volta 1. And yeah, this design accomplished to remove 39% of the sodium in the medium. That's almost 5 times the accumulation the wild type accomplished. And just to give you an impression, we also tested various other combinations of mutations and single mutations to learn more about the systems behind them.
Now, our practices with industries have shown that not only sodium, but chloride is an issue to be solved in chemical industry wastewaters.
So, what about chloride? Literature showed that chloride and sodium uptake were actually coupled, so we figured we'd just measure the chloride uptake and see whether, whether it would increase. And as you can see, it did. So, but without us even changing any of the underlying systems. So we see that this as a future application, since there's still a lot of potential.
So we successfully modified our yeast to take up more sodium and chloride ions, thus showing that our microbial system can be used for water desalination and purification. But our project still offers many more opportunities which could be investigated further in the future.
Our cooperating partners drew our attention to additional ions like potassium, and therefore we took up the task to create a new salt wort which is capable of taking up potassium instead of sodium.
So, 1 efflux knockout, 1 vacuolar potassium channel overexpression, and our early tests showed that already 18% of potassium had been removed from the medium. This proof of concept leads to the conclusion that our system could be used for all kinds of applications. The first goal would be to optimize our system for a concrete application, like for example in wastewater treatment plants with certain concentrations of sodium, potassium and possible other ions contained in the water. So, to reach this, it would be necessary to build a lab-scale test plant for conducting first experiments and investigating the growth behavior of our yeast under the respective conditions before upscaling the whole system. The implementation of our project, even only in lab scale, requires quite a lot of hardware devices, like pumps and membrane systems. Buying hardware can quickly get expensive, a problem many iGEM teams encounter. So our university, the RWTH Aachen, has a long-lasting tradition in engineering. That's why the last iGEM teams of Aachen already worked on solving this issue by developing cheap DIY devices, which we call tech bricks. The tech brick we have developed this year is a 3D printed peristaltic dosing system, or for short just our pump. Very importantly, it works with high precision, with a variance of only 2% at 100 microliter. It also possesses a digital interface and can be remote controlled via computer, so it can be integrated in LabVIEW. But the biggest advantage is surely the price, which is less than $95. We already tested the pump, among others, for membrane experiments, and we weren't the only ones who were delighted. Many people from the lab we were working in inquired about our pump and wanted to build one themselves. So, correspondent to the iGEM philosophy of get, give, and share, of course we want to motivate other people and iGEM teams to use and rebuild our device. That's why we are not only providing construction and user manuals open source, but we are also giving 2 pumps away for free. So if you're interested, make sure to stop by at our poster or exhibition space. Now, having proven the concept of our microbial desalination system and also tested its applicability, the vision of our project seems to be within reach, to develop a microbial supercollector. There's already a huge range of well-documented transporters from plants available, and by taking the respective transporters from plants and integrating them into yeast, we can adapt our method to the various pollutants.
Throughout our human practices efforts, with industry, research and the general public, we have revealed the need for water purification from additional ions like potassium or chloride, sulfate or phosphate, organic molecules and even heavy metals to be taken up by our highly specific salt vaults. And with this high specificity, new applications, like for example the recovery of catalysis or biomining, further enhance the potential our microbial supercollectors have.
On top of that, we can take our concept to a whole new level, using protein engineering and creating novel transporters for new kinds of substances. So the potential to extend our system is basically unlimited. During the last months, we have proven that our concept works, and we have already created 2 microbial supercollectors. We were only able to reach this as a team, working together and motivating each other throughout all setbacks and failures. So our team consists of 16 students from different academic backgrounds who all contributed individually to our project. But of course, we also had help. So we want to express our thanks to our advisors and supervisors who took part in our project and assisted us, and of course to our supporters who helped realizing the salt vault idea. So we hope that you have enjoyed our presentation. Thank you all for coming, and please feel free to ask any questions you have.
Okay, thanks again for a beautiful presentation. I really enjoyed your wiki and all of the videos that you guys put together. Seems like you've done a tremendous amount of work, so good job for that. My question is related to the Arabidopsis genes that you expressed in Saccharomyces. Did you do any codon optimization of those genes?
So we selected 2 genes. One was ATNHX-S1. It was of course codon optimized, but also we changed the regulation and deleted the C terminus to guarantee that the efficiency is maximized all the time, not dependent on the pH or calcium concentration in the vacuole. So we also codon optimized. The same was done to AVP1, the proton pyrophosphatase.
Okay, thank you.
So, congratulations. I have, well, 2 hopefully quick questions. So one of them is, I can understand from a modeling perspective that it's super convenient to have the membrane potential constant, but isn't that a bit, aren't you afraid that then your model is not going to capture the sort of like physiological reality of the cells?
Well, that was one of the questions we couldn't write it in the wiki because at the modeling page it was a little bit tricky and it was like right before the wiki freeze. Nonetheless, we integrated in the model, like the idea of the model was to integrate these different parameters, the pH and the changing potential of the membrane. We also wanted to integrate, but in the presentation there wasn't enough time to show it. But like for different channels, such as the chloride channels, we integrated throughout potential, gated potential, because that's what we found in the literature. The transporter that we use here were just like gradient driven and didn't need the membrane dependency, but the chloride did, and that's what we wanted to also model in the whole simulation.
In the wiki you state that you model it as a constant. So you say that it has a value that you got from literature, but it's constant.
Oh,
but if you are varying the concentration of protons, your membrane potential is not constant.
Yeah, but then the chloride, that's a point that we wanted to. The channel, the chloride channel, just works as a, how to say it, as a constant, like regarding the paper, the literature that we got to, the chloride just functions to maintain this constant membrane potential, the chloride channel that we found out. And it follows the gradient of the protons that go inside, or from the cations that go inside. Sodium,
we can discuss this later on.
Yeah,
so
that would be perfect.
If you don't mind, just a very quick one. So also something which is, how do you think, so like these overexpressions that you do, some of them they actually make the cells grow slower. So why do you think that then these sort of like super collectors will be stable? Why won't you have sort of like in one of these reactors simply a cell that doesn't produce one of these super collector systems and then kind of like just grows without collecting? See what I mean?
Like, you mean if we did just one super collector for many substances and then it doesn't grow? Because like this whole substances...
So some of the interventions that you do are based on overexpressions.
Yeah, they are.
But some of these overexpressions actually lead to a drop in growth rate.
Yeah.
So if you simply silence by, mutation, random mutation, the promoter, so during replication, during growth, then they won't collect anymore. But they will still outcompete.
Okay, I understand the question.
Okay, well, one solution to that we thought of was that we grow, like in an application, we would grow the yeast separately. So we would, like, due to our maintenance of the application, would ensure that the mutation tests would be stable. But yeah, we could have like an additional approach to integrate the sodium uptake more into the metabolism to prevent this, but we would like do this through the application.
Yeah, I think we understand what you're trying to communicate here. Yeah, that you would grow the organism, and then once it was grown up, then you would add it to your process, right? So the maintenance of the organism would occur outside of the process itself, correct?
Have you considered the energy problems? You use how much energy to grow the yeast and to remove the several amount of ions. Do you think it is economic sense to use so much energy to grow the yeast and remove this amount of ions?
Of course, that depends strongly on the application, but we try to measure like effectiveness or efficiency in another way. But that would be like a whole new project. But we found that you only need fairly small amounts of yeast to remove a notable amount of sodium. So in these experiments, like the dry weight of our cells is about 5 grams per liter, so it's fairly low.
In addition to that, if you talk about efficiency, you always can measure it in pilot plant. So you need pilot plant scale to actually get a certain amount to get a number and see is it efficient enough. but we actually talked to experts about that, and they said it's not realistic in the amount of time we've got. So that's something for the future, and it's not possible with the amount of time and financial situation of our team. So scale up is always necessary to actually get an amount or get a number to the efficiency.
Okay, thank you. I think maybe also you should talk to the team from WashU and borrow their UV light box, and you could grow your yeast in high concentrations of these different ions and then randomly mutate a lot of the genes that would increase halo tolerance. So good teamwork for the future. All right, thank you guys. Good presentation.
Thank you.